going to be attacking this monstrosity of an integral today, and you're going to find its amazing and beautiful result. Now, first things first, we're going to go with old Feynman's technique, and we're going to differentiate under the curve. Now, first things first, we have to define our new integral as I. This is going to be our integral. Now, we're going to introduce a new parameter, I of alpha, because I love alpha, you know, as you do. Now, we're going to put our new variable inside of our cosine function. We have cosine of alpha x divided by x squared plus 1. Now the reason we're putting the alpha here instead of at the bottom is because when we differentiate with respect to alpha, we get an x on the outside, and then we can make it all nicer and then at some point cancel out with the bottom. Now, but if we put the alpha in here, then you know it's just not fun, because we get 2's and it doesn't really simplify anything. So now what we're going to do is we're going to differentiate with respect to alpha, and we're going to get the negative integral from negative infinity to infinity of x times sine of alpha x divided by x squared plus 1 dx. Now what we're going to do is we're going to simplify this whole thing, or make it more complicated, and times the top and the bottom by x. Well, we're essentially timesing it by 1, but if we times the top and the bottom by x, this becomes x squared, and we're just timesing this by x. So then that becomes the negative integral from negative infinity to infinity of x squared sine of alpha x divided by x times x squared plus 1 dx. Now what we can do is we can plus and minus 1. So we're essentially just adding 0, but we're making, you know, a lot easier to factor everything. So we get the negative out front, and we have the integral from negative infinity to infinity of x squared plus 1 minus 1 of sine of alpha x divided by x times x squared plus 1. Now what we can do is we can factor this whole thing out. Now what we get in the end is we get the negative integral from negative infinity to infinity of sine of alpha x divided by x. And then we minus, but because we already have a minus at the front, we're going to plus. Okay, so now, so we were doing minusing, as we have here, because we were minusing the sine of alpha x divided by x times x squared plus 1. But because we have this minus, we have that minus, and that minus is put on everything, it becomes a plus. So we have plus the integral from negative infinity to positive infinity of sine of alpha x divided by x times x squared plus 1 dx. Now what we notice here is we know the value of this integral. We've solved this before. Now this integral evaluates to pi, and so that makes that negative pi. Now no matter this value, provided that it is not 0, and we know it's not 0 because we're going to be plugging in n as 1 to get our original integral. So I of 1 is equal to our original integral. So we know that this is a non-zero value. So that gives us negative pi plus the integral from negative infinity to positive infinity of sine of alpha x divided by x times x squared plus 1 dx. Now what we're going to do is we're going to take the derivative again. Try and simplify this whole thing. Now, so we get the I double prime of alpha is equal to the integral from negative infinity to positive infinity of x times cosine of alpha x divided by x times x squared plus 1. Now we notice that these x's cancel, and that this is equal to our original equation. So we get this differential equation of I of alpha is equal to I double prime of alpha, and this is our differential equation. So now we could use the Laplace transform to solve this, but there's a simpler and much easier way that we could do this, and we could just let I of alpha equal some exponents. So we're going to have c to the times e to the power of alpha times beta. Now, this is the generic form of an exponent. It's some constant times some value times our variable. Now, with that, we're going to take the derivative twice to get our expression for I double prime of alpha. And what you can see when we take the derivative of something to e to the power of something, it's just that times its derivative. And because we're doing it twice, we're getting I double prime of alpha is equal to c beta squared times e to the alpha beta. Now, we can rewrite this. We already have our equation here. So what we're going to have is we're going to have c beta squared times e to the alpha beta minus c to the e alpha beta equals 0. And so now we can factor out c e to the alpha beta, and we get c e to the alpha beta times beta squared minus 1 equals 0. And from this we get that beta is equal to plus or minus 1. Now, because we have two values here, we must have two values within our equation. We can't have this just being plus or minus 1. So what we're going to do is we're going to have I of alpha is going to be equal to c to the e alpha plus c to the e negative alpha. So that way we have our positive and our negative. And now this doesn't matter that we're plotting them together, and that is our operation, because that will be changed based on our constants. So we're going to have two constants, c1 and c2. Now these will change in order to accommodate for this addition. Now, as a result of doing that, we need to be able to solve for c. Now, how we're going to do that is we have to find our initial conditions. So, our initial conditions for I of 0. Now, what is I of 0? Well, when cosine of 0 is just 1 divided by x squared plus 1, well, the integral of that is just inverse tangent of x. And so we know that the inverse tangent of x from negative infinity to positive infinity, all of that just equals to pi. So we say that I of 0 is equal to pi. And now we want I prime of 0 is equal to, well, let's see, where is our I prime? Our I prime is here. So, but what happens when we have sine of 0? Well, sine of 0 is just 0, and 0 divided by that is 0. So what we just get is we get our value here of negative pi. And now we have our values, and we can solve for them. So we have c1 plus c2 equals pi, because e to the 0 is just 1, and e to the negative 0 is also just 1. We have this equation, and now we take the derivative, we get I prime of alpha is equal to c1 e to the power of alpha minus c2 e to the power of negative alpha. And we plug in 0 at the top there, and we just get c1 minus c2 equals negative pi. And now with this, we can plus these two together, and we get that 2c1 equals 0, which means c1 is equal to 0. And if we plug that into our equation, c1 equals 0, well, that means that c2 is just pi. c2 equals pi. So now we have our thing of times e to the alpha, which is our equation here, but that just cancels out because we have the 0 here. So we get that wrong equation. We have our c1 here, so that just cancels this out because we're timesing it by 0. So we get that I of alpha is equal to pi times e to the negative alpha. Now this is our equation for our thing here. Now what did we say was equal to our equation when alpha was a certain number? Well, we said that when alpha is equal to 1, that is equal to our original integral, because 1 times x is just x, and cosine of x divided by x squared plus 1 is our original integral. So we said when alpha is equal to 1, or when I of 1, we get our value of pi times e to the negative 1, which is just equal to pi divided by e. Therefore, we can say that our integral, the integral from negative infinity to positive infinity of cosine of x divided by x squared plus 1 is equal to pi divided by e, e being Euler's constant. There you go.